Hey, and welcome back. This is the last couple of sections here, spanning tree configuration and first hop redundancy protocols. By now you've probably done a couple of labs for a configuration, but this is just a little more detail on how that happens. And then as we go on, the last part, first hop redundancy protocols, isn't really about spanning tree, but I think that's a section we just didn't know where else to put it in the curriculum. So we're going to look at it here. So I'm going to go away and we get started here. This page points out the default configurations on a 2960. This is the switch that we're using in the NetLab labs, and a lot of people use on any of the labs at school. Just to review a little bit, we have right here the spanning tree VLAN port costs. 1000 megabits, the cost is 4, and it's a low cost because we value high speed. 100 megabits, which used to be screaming, is now just average. That's 19. That's the average port, 100 megabits. And if you have a 10 megabit port somewhere, then the port cost would be 100, making it not preferable at all to spanning tree. Sometimes you'll look at timers, especially if we do a debug of spanning tree. We'll see that the hello timers run every 2 seconds. And then they have a forward delay time of 15 seconds. That means if we haven't in 15 seconds, if it hasn't heard anything, there won't be any more forwarding. Aging time of 20 seconds. All right. So the BPDUs, the hello time, etc., all of that has to be functioning in order for spanning tree to stay up and operative. If it doesn't hear back from a hello timer, it shuts down and changes states and recalculates. Doing the bridge ID and PVST plus, a couple of ways to do it. We can do, and the details are in the chapter, but you can either tell it, this is by VLAN, remember. We did the whole switch before. They were global configurations, but now we go by VLAN. Of course, all the switches we're using with have only one VLAN to start with. So we do VLAN 1 root primary, and then that will set that up as the one there. And the way that happens is in the background. It sets it up with a priority number that will be lower than all of the others. And then you can also do it by assigning a specific number of priority. The formula for that you'll read about. And setting up a secondary as well. And so if you have a primary and a secondary, those are the two switches that will be used to do the STP calculations. You might want to do that if you have specific switches that you think are good or just part of the network where you show it to be optimal. And I know this is old by now, but when you do a show spanning tree, or show span actually is the truncated version that'll work, here's what you're looking for. This bridge is the root, and it's got its priority number, 24577, which is 24576 plus 1 because the VLAN number is added to it. Remember that. And because it's the priority, both ports are in forwarding states. Now, port fast, we mentioned earlier, when it's on the edge of the network with the access layer or edge port, PC1, PC2, PC3 can have port fast, and that is when you configure a port to come up without running the spanning tree process, because you're confident that there won't ever be a switch put onto that port, and it's only going to be used for access layer and edge routers. So by installing spanning tree port fast, a switch can power down and come up, and there's no 40-second wait. Right as the switch comes on, they'll go right into the forwarding state. All right. Now, BPDU guard is another thing. Now, remember, BPDUs are the hello time protocols that switches exchange with each other. So you want to put in a BPDU guard, because that way if a switch ever does get mistakenly put in to those ports, at the reception of a BPDU, it'll be thrown into error disable state, which is a true shutdown. And when it's in error disable, you have to manually go in and fix it. We'll see that in a couple of things that happen with switches. So the BPDU guard protects the spanning tree process by assuring that another switch won't ever be put in. Now, PVST load balancing, this is a way of configuring different switches to be root ports for different VLANs. We saw how to set a priority, primary and secondary priorities. This is how you can do it for per VLAN. So over here in the example, you have spanning tree VLAN 20 root primary. That's on switch 3. And on switch 3, you're running VLAN 10 secondary. So it's a backup if it needs it. But down here on switch 1, VLAN 10 root, VLAN 10, the root is switch 1 and the secondary is 2. So it's fairly simple to configure, but you better have a plan in place before you start doing this. So the load balancing, this is just a different method to specify root bridge, and that's to be setting the priorities equally as 4096, because that is the calculation that the switch understands in multiples. And when you do a show running config, because remember those are global configurations, not interface, so the span and the running configuration, it'll tell you which VLAN has which priority. Okay. Now, when you're implementing STP, it gets complicated and you have to make sure it's running right. So here's a flow chart on the left on the analysis, and you do a show CDP neighbors command to make sure that everything's connected in the right space. This is getting back to the first class, but the CDP neighbors, that Cisco discovery protocol, will help you make sure that all the switches are plugged in to the ports you wanted them and what they're using. All right, and then the show spanning tree VLAN will tell you where all the root bridges are. All right, and you want to make sure where the root bridge is and the layer 2 path all around. So you want to have a diagram and make sure the diagram matches the reality of your network. And so you take your topology and you match it with the output on your show spanning tree VLAN, and make sure all the blocking ports, the designated and the roots, are the ones that you had in mind. Now, again, if spanning tree fails, if a switch gets put onto the network that isn't spanning tree and there's a loop, or if a port, like in the example here, the S4 gets put into one of the interfaces gets put into forwarding mode by mistake, here it's blocking and down here it's forwarding, you'll end up with the crash, with the broadcast storm, and everything will go around. All right. Now, if that happens, just bringing the links back up isn't going to do any good. So you need to manually go through and unplug your redundant links, get it up and running again, and then go back and figure out what happened. So you have to physically break the loop so that the network will come back up, and then implement spanning tree once again. Now, to move on to our second part about the first hop redundancy protocols, again, not quite spanning tree, but somewhat related. If a PC can't get to the default gateway, and then it can't communicate with other networks, all right, it has to have a default gateway. And if a router goes down, and there's no redundant default gateway, even if you have redundant routers, if the default gateway goes down, it still can't it still can't find the edge and get out to another network. So in this diagram, we have lots of redundant routers here, route switches, but PC1 only has a default gateway of right here on R1. If R1 goes down, it'll still have access to other routers, but without a default gateway. And what's it going to do? All right, so we have 10.1.10.2 and 10.1.10.3. If the default gateway doesn't match, it's not going anywhere. So the way around that is to create a virtual layer of routing. Not virtual, I mean, they're virtual routers in one sense, but actually this is a virtual MAC and virtual IP address. And that spans over 2 or 3 routers, depending, or however many routers you need in your area. And then if one fails, then the other router picks up that virtual IP address, and the edge, the access layer, can still communicate with it. So it's not a physical connection, but it's a virtual IP address sitting on a physical machine, but both machines have the same virtual IP, but only one's running. And while they're actually both running, only one is actively forwarding traffic through the virtual router interface. Now, those first hop redundancy protocols, here's a list of them. HSRP for IPv4 and IPv6, and then the virtual router redundancy protocol for versions 2 and 3, same thing. And then the gateway load balancing protocol, I'll talk about that in just a moment, and that runs for 2 versions as well. And then there's an ICMP router discovery, which we won't be getting into. But here is a different look at what happens in this topology. We have 2 active routers connected to the network, and the PCs, if there's an emergency, will be able to use either one going out. So both active routers configure a common virtual IP and MAC address, along with configuring the HSRP protocol. All right. And when that happens, so it looks on the network like it's going out there the whole time. So in the show standby, we see there's a virtual IP address of 10.1.0.20, and the standby router is 10.1.0.6. That's the physical IP address. All right. We have a secondary virtual IP address of 21, etc., but we'll configure those in the lab. Now, gateway load balancing protocol, instead of one router not forwarding at all and the other router doing all the work, this protocol allows for both of them to load balance through that virtual interface, and if one fails, then the balancing just all shifts to one. So it's a way for it to actively load balance traffic and be a little bit more efficient. So there you are. That's our introduction to switching. I hope you enjoy the labs, and we'll see you in class. Thanks so much.